Howdy folks. For this video, we're now going to look at enthalpy of formation values and how to do simple reactions, how to do reactions where we don't have to combine multiple equations together. This is probably the easier aspect of this chapter. I might look at some various different ways to do this. And so that's where we're going to finish up. Now, enthalpy can be directly applied to a compound. It doesn't have to be applied to a reaction as a whole. We can look at the enthalpy of a given compound and imagine that as the potential energy stored within that compound. So with that in mind, we get the following term, the standard enthalpy of formation. So delta H means the enthalpy, the change in enthalpy. The circle as a superscript means it's standard, meaning this is done at standard state conditions, and I'll talk about that more in a second. And the little f stands for formation. So it's the standard, the energy to form a compound under a standard set of conditions. How much energy does it take to form this one thing? Now, most things will have a negative energy, meaning it produces energy to form. However, there are some things that will consume energy to form, meaning they are metastable and they really don't want to form. But most things will produce energy when they're forming. And so this is the energy either required or produced in forming 1 mole of a compound out of its component elements. How much energy does it take to form 1 mole of CO out of carbon and oxygen? How much energy does it take to form 1 mole of formaldehyde out of carbon, hydrogen, and oxygen? How much energy does it take to form 1 mole of iron 3 oxide out of iron and oxygen? Doesn't matter what we're forming, it's out of its component elements. Because of the nature of this, the simplest form of this is calculating the enthalpy of a pure element in its standard state. Now, since a pure element in its standard state is how it exists naturally, you're basically looking at how much energy does it take to get from point A to point A. Since there is no change here in our starting point and our ending point, no energy should be required. This is the most stable form, so it will take no energy for this to occur. So all enthalpy of formations for elements are 0. Please note this is elements in their standard state. If I'm looking at liquid hydrogen or solid hydrogen, those are not the standard forms of hydrogen. If I'm looking at monoatomic oxygen or ozone, those are not the standard forms of oxygen. It's always O2. So those aren't the standard states. So you got to remember, states of matter and the atomic combinations must be taken into account. But the pure energy and the standard states are 0. So to make an enthalpy of formation, we'll take the component elements and we can figure out the energy to form them. So for example, water liquid forming out of hydrogen and 1/2 mole of oxygen is negative 285.83. This is the one time it is acceptable to have fractions as a coefficient. Why? Because the enthalpy of formation is the energy to form 1 mole of water. We could easily calculate this for 2 moles of water, but we are purposely not, because of the fact of the definition. So if I want to calculate magnesium oxide, it would be 1 magnesium, 1/2 mole of oxygen, and that produces 601.8 kilojoules to produce magnesium oxide. Now, every chemistry textbook worth its darn will have an appendix that will have a large number of enthalpy of formation values for elements in them. They will have them elements and compounds in various states, and you can look them up and find these values. Whenever you're doing a problem on homework, you may have to consult the appendix. You cannot be expected to know these guys except for pure elements. All these other guys must be looked up, and I wouldn't have it any other way. So how do we calculate our enthalpy of reaction using this new knowledge? Well, in Appendix C, we'll use the number of enthalpy of formation values. Well, the enthalpy of a reaction is equal to the sigma, which is sum of the change in enthalpy of formations of all the products, minus the sigma, which is the sum of all the enthalpy of formations for all the reactants. So looking at a chemical reaction, we sum up our enthalpy of formations on the right, we sum up our enthalpy of formations on the left, and we subtract the left from the right. Final from the initial. Because what is a change? A change is how much different is the final from the initial. So looking at this, sodium chloride is 407.1. There's 1 sodium chloride. Water is 285.83. There's 1 water. So the total number of products are negative 692. I add up the reactants. HCl is 167. NaOH is 469. And the total amount of products is negative 636. So the difference between the products and the reactants, I'm subtracting a negative, which means the same as adding a positive, we get a negative 56. So even though these were very big numbers, this reaction only produces 56 kilojoules of heat. But that's still a good deal lot. So, with that in mind, let's look at this reaction. 2 nitric acids plus lead carbonate goes to water and CO2 and lead nitrate. Now, on a real problem, you might actually have to look up these values, but I got these here. 206.6. Lead carbonate is negative 699.1. 285.83. 394.4 and negative 421.3. Okay. Okay, with that in mind. Now, we're going to find the total sum of all the products. 285.83, negative 394.4, negative 421.3. So the total amount of products is negative 1101.53. That's fine. Now here's the important thing. There's 2 nitric acids. So I have to multiply my nitric acid by 2, because I'm doubling the amount of them. And then we add our negative 699.1, and the products, the reactants are negative 1112.3. So enthalpy is products minus reactions. When we're subtracting a negative, it's the same as adding a positive. One, 1.53, and so we get positive 10.77 kilojoules. Positive 10.77. And what does that mean? That just means we have absorbed some energy. Our solution would have gotten warmer. What the surrounding water would have gone colder to make this work, to make the reaction run. And so being able to do this is a key thing. Being able to do this is a big part of this chapter. So common enthalpy reactions you'll see in your everyday life. Hot packs. Instant hot packs, something where you just break them open and they heat up real fast. Well, some of which hot packs work under these simple reactions. Iron plus oxygen, it's just rapidly rusting, and it's producing approximately 1,648.4 kilojoules worth of heat to do this per that reaction. Or you could do calcium chloride in your blister pack and breaking it and let it dissolve in a bunch of water. And that produces a lot less, but it's just dissolving this salt in water. You don't need iron powders, and you don't need to rapidly heat this up. And for reversible one, a reversible one is a rapid crystallization. When I flip this in a supersaturated solution, sodium acetate will crystallize and incorporate water into it and produce negative 18.5 kilojoules of heat. Of course, that one you can easily warm it back up and re-dissolve it. And as long as you let it cool, it will go back to its original state. Instant cold packs can work under a similar function. We can dissolve magnesium sulfate heptahydrate and allow that to dissolve and produce water and magnesium sulfate, and it absorbs 13.2 kilojoules of heat. Or we could just allow ammonium nitrate to dissolve in water, and it will absorb 25.8 kilojoules of heat. These are simple things. You blister packs, you allow water to mix, and as it dissolves, it just absorbs heat because it takes energy to break up the crystal structure. And so where's it going to grab that energy from? It's going to grab it from you, me, the surroundings, everything that's nearby. And so that's how that's going to work. Now, the last little bit is about bond enthalpy and lattice energies. We'll keep going with this. Bond enthalpy is just an alternative way to measure the reaction enthalpy. Is by calculating the energies of relative bonds. Every bond broken requires a certain amount of energy cost to break that bond. Breaking bonds are naturally endothermic. They're stuck together. It takes energy to pull these atoms apart. I know this is harder to imagine, but when they snap back together, they are producing energy through molecular stabilization. Making bonds is always exothermic. Now, the energy associated with these bonds are related to the bond lengths and the number of bonds between those two atoms. So bond length and bond strength. The farther away they are, the less attractive forces. The average bond energy of each bond type has been tabulated and presented. Now, these values are averages, meaning every OH bond is not all the same, but they're close enough that you'll get close enough to the real value. Now, because these are average values, reaction enthalpies calculated by this method may differ from those calculated by the standard method. That's to do with the average. But to calculate the bond enthalpy, you need to consider the Lewis structures, but the way is simple. We add up all the bonds broken, which is the cost, and we add up all the new bonds formed, and subtract bonds formed from bonds broken. Now, this is the opposite method from our standard enthalpy of reaction, where products minus reactants. Now it's, because all these are positive numbers rather than negative numbers, it's reactants minus products. But looking at this, methane burns an oxygen to form CO2 and water. Look at these structures. So we have the Lewis structure of methane is 4 hydrogens bound to CH and 2 OO double bonds. It forms 2 CO double bonds and 4 new OH bonds. So I'm looking at the bonds broken, bonds formed. All the bonds are broken, all new bonds are forming. So hydrogen CH right here is 410. There's 4 of them. For O2, 498, there's 2 of them of OO double bond. 745, there's 2 of them for C double bond O right there. And 460 for OH, there's 4 of them there. And if we calculate this, this is something like negative 694 kilojoules. Now, mind you, this is rather different from the value you would get if you did it through the enthalpy of reaction of negative 802. However, oxygen actually exists somewhere between a double and a single bond. So to use the double OO value is maybe not the best option. So that's where it kind of can goof up a little bit. But we won't really go into that right now. But the last thing is lattice energy. So the energy associated with making a solid. So if we calculate the formation energy for ionic solids using what we call the Born-Haber cycle, which is if I mixed, say, a metal with a halogen gas, and use that to form the metal salt, and we use to calculate the energy. And we calculate it through a series of intermediate steps. So basically, the metal plus a halogen salt produces a buttload of energy. Well, if you try to break it down into each individual step, you see something weird. Well, in order to make this react, let's turn it into a gas. So it absorbs energy to sublimate. Then to ionize it, well, we have the ionization energy, so we calculate that. We have to split the halogen from a diatomic into a monoatomic. That takes energy. We've done that. Okay, time to get some energy back by electron affinity. Well, that just puts us here. We are here. We started there, and we need to figure out how we get from here to here. And that is where the lattice energy comes in. The 2 charged particles in the gas phase are not particularly stable, but putting them together, sticking them together as a solid, generates so much energy that it brings it from like deep in the red to well in the black. It's like having 5 Black Friday specials in a row. We're just suddenly, boom, we went from we're going to lose out to we're winning. This energy of stabilization brings this back we've gained energy. This is what we call the lattice energy, the energy we get by weaving these cations and anions into the crystalline solid. Now, this lattice energy is so strong it will make formation of a solid into a highly exothermic process. Lattice energy depends on how well the ions pack and the attraction of the ions. So remember, positive and negative are trying to stick together. So the closer we can stick them together, the more attraction. The more positive or the more negative, the more attraction. So lattice energy is directly related to the relative charges and the bond distance away from each other. The equation is actually the lattice energy is equal to kappa, which is a constant, times the charge of the cation times the charge of the anion divided by the bond distance between them. Now, while I will never ask you to directly calculate this by itself, often what gets asked is a comparison of lattice energies. Generally speaking, as the charge increases, the lattice energy increases greatly because the size, and there's a direct dependence on the size going down and the charge doubling that greatly increases our lattice energy. However, if you're comparing atoms within the same column, as the molecules get larger, the lattice energy tends to decrease ever so slightly. So look at lithium chloride versus sodium chloride. Lithium is smaller, 861. Sodium is a little bit bigger, 788. Potassium is bigger still, 717, 692, 658. They're basically getting bigger, and so the lattice energy is going down. Sodium fluoride is the smallest molecule, 931. Going all the way to sodium iodide is 673. So as the cation or anion increases, lattice energy tends to decrease. However, if we look at lithium fluoride from magnesium oxide, the bond lengths of these molecules are essentially the same. So there's not a huge change here, but look at the energies associated with this. The bond energy of lithium fluoride is negative 1046. Okay. 1046. And yet, when I put these two together, these negative 3850. It is nearly quadrupled. Not quite quadrupled, but nearly quadrupled, because Mg is 2 plus, O is 2 minus. 2 times 2 is 4. 4 is our quadruple effect. So if I just look at the relative charges make the biggest impact. But that is this chapter. It's a little bit tricky chapter, but hopefully it was reasonable. Thank you. Have a good day.